Voilà. Donc,
merci beaucoup David, merci tout le monde, je suis très heureux d'être là. Donc peut-être je vais parler en anglais, ok? Bien sûr, on peut discuter en français, etc. So this is two talks. It's part of it is contains in my recent book of 2014, Axiomatic Method and Category Theory, and some new stuff which mostly presented in a paper which finally accepted. It was a long story with called on Constructive Axiomatic Method. So. This will be two parts, and today will be mostly historical on Euclid and on Hilbert. Basically, I'm going to compare two frameworks. Hilbert, I'll try to make it historical Hilbert, but I take Hilbert to be very much as a paradigm, as a pattern of axiomatic method as it is mostly known today, not necessarily practiced, but at least theoretical idea of axiomatic of today's axiomatic method very much goes back to Hilbert, and actually my main aim is to change this view. So before I begin with Euclid, I give very little overview of the whole thing of two parts. And so my claim, which I'll try to defend, is that received notion of axiomatic theory stemming from Hilbert's work of Foundations of Geometry of 1899 is not adequate to the recent successful practice of axiomatizing mathematical theories, not completely adequate. In particular, the axiomatic architecture of elementary topos theory and even more clear, more obvious way, homotopy type theory does not fit into this pattern. So that will be a claim I'll try to defend and suggest alternative pattern. And at the same time, this alternative pattern will be not something absolutely, different from anything we know, because I'll try to show that topos theory and homotopy type theory both fall under a more general, in many respects, more traditional notion of axiomatic theory stemming from Euclid. So I make some parallels between, say, homotopy type theory and Euclid, not for saying that it's kind of coming back, but rather I see this as a, broader insight of what is axiomatic method, what is mathematical theory, and in this broader insight, it looks like what we know as formal axiomatic method from Hilbert just looks like, rather special approach, right? I'll try to make this picture bigger approach, and why this recent development like homotopy type theory are important, because this broad approach is not necessarily simply informal, something vague, as often argued in this Hilbertian tradition, right? That Hilbert, of course, recognizes that that Euclid made something different, but he would say he did something not really clear and informal, so forth. And now we do this more formal. And of course, homotopy type theory is formal, is a formal mathematics. So this argument does not go through. I'll try to show that there is kind of broader notion of axiomatic method, which I'm going to call constructive. This term, of course, is very much overloaded in logic and in mathematics, but I think this sense, which I actually borrow from Hilbert Elbernay's work on 1934, its first volume of Grundlagen der Mathematik, I think this is, this way of using word constructive just worth to be taken as most general, because you'll see, it's not like constructive, say in Markov sense, or in Bishop's specific sense, is indeed more general, and I believe that it really somehow catches what could be called the more generic notion of being constructive. Okay, so this is plan of today's talk. I'll talk on Euclid. I'll use this a little bit frivolous formula of doing and showing. Actually, I derive it from ending of Euclid, from this problematic of problem and theorems and Euclid and how they end, how you may formally always distinguish them. It's every theorem just finished with this formula what has to be proved, quod erat demonstrandum, and the problem with quod erat faciendum, right? So this, it's like, look like we do something and show this important. Okay, I'll show. This is not proving but showing. That's, I'll explain a bit later. So I talk about Hilbert. So I'll talk about this, I call it form and object. It's just kind of core problematic of his axiomatic approach. And later I would call about the so-called genetic method, which early in his career in 1900 he actually opposed to axiomatic method, but later in this work with Bernays and in some contemporary talks, he actually tended to synthesize. No, at least this is my reading. I tried to defend it. It was not very, how to say, explicit. Kind of synthesizes genetic and what he called axiomatic for exactly making what they called constructive. But Hilbert and Bernays never developed that. They just mentioned in the introduction. They never developed theory of this constructive method. It was only introductory remark. So I tried to do this, right, using topos theory and homotopy theory as examples. Right, and that maybe I'm going a little bit, I have time and until the 6th to structure better, so it's plan of second talk. I'll begin with talking about typing and Curry-Horvath correspondence. It would be very interesting also to mention some early developments of 19th and 18th century even, which kind of became marginal in beginning of 20th century because of Hilbert. But now they could be reconsidered. I mean, Leibniz's idea of geometrical characteristics and Brother Grassmann's work and Piana's work. But I will not have time, I think, because it's really, it's related, but it just needs more time. So, but perhaps I'll mention a little bit. Then I will use topos theory as example. No, actually, some work were done by people like Colin McClarty, we all know, to fit this axiomatic topos theory into, say, standard scheme, right? But I'll try to argue that there is kind of reasons and motivations by Bilovier, by his text, to do that differently. Not to do that, but using to use this broader framework which actually I'm looking for. And in homotopy type theory, that becomes much more clear. Then we have actually formal means to distinguish, say, what is proposition, what is not proposition, things like that. That, say, in topos theory we may only kind of guess, interpret, and here it becomes really explicit. And of course there are also a lot of problems. And that part, I don't know, perhaps I will not have time, but I do believe that, and that was also part, you'll see, of Hilbert thinking, that this form of axiomatic method, it's not just interesting on its own, and not just it's better accounts for existing what is called mathematical practice. Even I don't particularly like this term, I'll explain later. But also it could be better used, say, in physics, in sciences, for rather clear reason, and which was, of course, Hilbert's, as well known, one of his aims for the whole story of axiomatic method. But that's, again, I don't know, maybe have really time for that. Okay, so let's me begin. So that, again, before I come directly to Euclid, the issue is, what is a theory, right? So I'll try to show that this received view, which just says a theory is a set of propositions, statements, something which may have a truth value, right, truth evaluated, is a theory, is a set of propositions after all, right? Or statement. So perhaps some context people would talk about judgments, like Martin left. But and then axiomatized theory just amounts to distinguish some certain subset A of this proposition, certain rule of inference, which in one sense or another allow to generate the rest, right? It's like presentation of groups in group theory with relations. So you have some generic subset which in procedure which is logical inference, which allows you to infer further theorems. And of course there is much more nuances in all that story. And some of them I'll discuss later, right? When we distinguish between syntax and semantics. Here I think it's very interesting point, but because people talk about Wolfram formulas as if it would be purely syntactic idea, right? What is well formed. But of course behind there is this semantical idea that well formed formula is a proposition, not something else, right? It may have truth value. So and that, of course, already compatible with this idea, right? That what we need is a formula propositions, not something different.
A formula with a free variable. A formula with a free variable, as not with the.
Yeah. Or maybe right. There are some. No, actually, okay. There are here syntactic concept with semantic concept. We should distinguish all that. But I just mentioned that now. For saying that I'm really, my target is this, because I assume that this view, right, it's still valid in here. So this is some precision, some details which are built on that, right? And so my question now is to challenge this, and at that moment not go to these further details. We'll come to some of them. Okay, so claim, and that time I'd say historical claim, that Euclid's mathematics, for being more concrete, I just take first book of Elements, so it does not fit into this rough idea, I say, right? It's not a set of propositions. And if we try to present this in that way, we really lose the point. Of course, it's too loose, becomes too loose as interpretation. Okay, and here actually already after I published the book and this paper, and I found author who really expressed and very distinguished, who really said that, because I was puzzled how it's that. It's kind of obvious if you read Euclid more or less in detail. So how it happened that so many logicians, I spoke with that with late Jakob Hintiker, for example, and of course he had very interesting, very important ideas about how to reconstruct Euclid. But when I discussed him this point, I said, yeah, you may be right, but let's assume it's proposition. So and Jan Müller writes from his paper in 1980 something, I can put the year I have. So he says, I know of no logic which accounts for this inference. And inference is typical Euclidean. I'll give examples in a minute. In Euclidean formulation, one postulates that certain action is permissible and infers the doing of that. So he does it. An obvious analog of procedure is a relation between rules of inference and deduction. So his point, rules of logical inference are not proposition. Rule is not a proposition itself, even if it's in some meta language, of course, it can be given propositional form. Rules of but here he talks an analogy, right? Because in an analogy, I think and that will be key thing in homotopy type theory. Analogy is between inferring proposition from other proposition and building, say, object from other objects. So we have rules in both cases, and in homotopy type theory we'll see they are actually common. So it's the same rule which just applies for such specific case. But here there are different rules. So rules of inference permit certain moves described in a general way. So we infer disjunction, say, from from A. And deduction, he calls something different. Deduction, he calls that we obtain a new proposition. So he distinguishes a rule, kind of just rule of construction, right? And deduction as a, say, logical procedure obtaining proposition from proposition. The carrying out of this deductive step is certainly not itself inference, for neither the rule nor the step is a statement capable of truth or falsehood. Right, that's the key point, and I'll show that. And he says Euclid's postulates are not capable of truth or falsehood. And actually axioms, I will say too. We'll see.
Are your claim about postulate or postulate and axiom?
Here I think about postulates.
No,
but
Euler is on postulate, but your claim is about postulate or postulate
no,
and axiom?
frankly, until that point I claim about postulates.
Okay.
But now I think I may also try claim that about axioms as well. But that perhaps I will not defend today, if I should work on that. Euclid's construction are not inferences from his constructional postulates, they are actions done in accord with them. No, okay, now I just reminding here people who really in the topic, so but I make some short reminder on Euclid, and I'm sorry if some of you maybe know this better than me. So we have three kinds of first principles in first book, definitions which I will not discuss, I wrote my PhD on them, axioms, otherwise common notions, and finally postulates, right? And here are common notions. Postulates, I'll discuss only 1, 2, 3, because other postulates here. So this clearness, this clear picture which I'm going to present you is kind of distorted by postulate at least 4. No, fifth postulates I also will not discuss, but I think it enters the picture. With fourth is more difficult, but I will not discuss. So here are common notions, koine noia, you well known. No, I just replying to David's question, and but I will not go into that. Important point, and that we read in Proclus commentary, why they are common. They are called common. No, some historians say because it's kind of common knowledge, but I rather persuaded by those who say they are common for numbers and magnitudes. So they are only principles in Euclid which hold both for geometrical part and arithmetical part. In that respect, they are very special. And actually, that's separate work. I would like to really finish also paper on that. I think some people also claim that, not first, that actually Aristotle's idea of logical principle, of say perfect syllogism, which we today qualify, say, as a logical principle, as a rule of inference, right? It is kind of based on the same idea of Euclid's axiom, but it generalizes, because Aristotle wants to include into the picture something which is not mathematical, right? He does not believe that everything is ultimately mathematical, right? So he wants to say there are some entities, some, for doing physics, which are simply not mathematical, and for that reason he needs some broader notion of axiom. By the way, he calls his first syllogism axiom, and here how we may identify actually, that's why we call Euclid's axioms through Aristotle. At least that's historical justification for doing this, right? So axioms, they are not just propositions without proof, not in model sense. They are logical principles, and in that sense we may say they are not propositions like rule of inference. Of course, in the form expressed by Euclid, they do look like proposition. I like postulate, I'll show, right? So they have this grammatical form of proposition, but if we take seriously the idea that they work as kind of logical rules, but logic would be sort of regional. So it will not be logic for everything, but just logic for mathematics, right? But perhaps for, you may, of course, using Plato and so on, develop ontology where you don't have anything else, right? Everything is ultimately geometrical or arithmetical. So that, but Aristotle think that that ontology is wrong, and that's why he kind of develops. And I have some textual evidences for that, but I think I'll skip. Maybe if you would like, we may do this in discussion time. So there are really questions where I believe Aristotle says exactly that. Okay, but now it's I think more clear cases, postulates. You see in by the way, translation in English is very good, his translation in that respect, because I think in Russian, for example, we also use kind of model rendering. It is possible to produce, right? And in that way, you make it propositional. Or if you say, as say more standard formalization, given to point there exists a line, you make kind of existential proposition, right? But in Euclid's, it's neither. It's not proposition. You see, it's express an infinitive verb. And I don't know. By the way, if you do it in Russian, that would sound as an imperative, as an order. Do that, right? I think in English there is no that concept, right? I spoke with like experts in Greek. They say in Greek neither. So it's just kind of indeed abstract idea of say operation, and kind of evidence also for that. I think that you may also analyze them as operation in say modern sense. They all have not only output, something exists or it's possible to produce, but they all have input. So you input to point, you output segment. You input stride. No, this of course is kind of not very determined operation, right? You input a segment and you output a longer segment. But how much longer, it's up to you, so to speak. No, and third postulate of course, you input a segment again and output a circle. And the only circle in that case, because to transport it, it's already a problem. It's not in postulate itself. Right?
This is a constructive reading of the postulate.
Right.
I had a discussion with Marco about that, because if the third was true, can you go back? So you will not have a proposition asking for, given a circle, find its center. Because any circle will be constructed with a center.
No. I may reply to that. I may reply. You want now?
Yes, yes, sure.
Yeah? No, my reply about that, because it is a mistake to say that it's like, I think Becker had this idea, Oscar Becker, that basically they work as a existential, axiom. So everything which is you theorize about must be first be constructed, and that is false, and that does not follow from this postulate. You do have definition of circle, and that's enough. You see, to ask that question.
Okay.
You does not require that you cannot talk about circle without producing it first.
Okay, so it's not this interpretation of constructive that you're using. It's another.
No, it's different sense if you like.
Because Marco used constructive in the sense that I.
No, I think that has been. No, there are a lot of places where you show that can.
I agree.
Yeah, sure. So right, you may put these things into proposition, but then it's really kind of you should kind of violate the text and go very far outside the text. So in that sense, this reading is kind of straightforward. And of course, it already shows that it does not quite fit this picture of theory as just system set of propositions, right? And now we come to these problems and theorems. It's again simply a short reminder that they have common structure. You may describe this explicitly in Proclus, but also it's indeed, if you take at least Hilbert's text, it's really there. So in that sense, it's very close to text. So every, by the way, this word proposition, when we say proposition 1, proposition 2 in Euclid, is absent from the text. It's just added by editor, by us. Well, maybe it's long traditions, Hilbert was not the first one who created, but it's absent from the text. There is no this general term for both problems and theorems. They're just numbered, 1, 2, 3, like this, right? But interestingly, that I'll come in a minute what is problem and theorem, but they have the same structure, even if kind of epistemically, so-called, the idea of theorem and a problem looks like quite different, but logically they have the same structure. So we have enunciation, exposition, specification, construction, and proof and conclusion. You see that proof in this narrow sense just is one part among between 6, right? It's not like proposition proof as we rather consider it today, right? And okay, here it's, by the way, this is the, I think, first or second theorem in the order, because it begins with problems and the elements, and it ends up with problems. By the way, also that shows that this idea that problem is something preliminary, right, to make a stage, it's just wrong. The last proposition is a problem, how to construct a regular polyeder. But that's typical problem. So I will not go to these details. They're elementary. So first you say certain facts. So it's a theorem. Then exposition. Was, by the way, attracted Hinticke's attention a lot. Of course, all Kant's problematic is here. So we kind of instantiate. That's today's logical term for what is going on here. So we kind of apply this proposition to individual case, not a specific case, but individual. We say, we claim something about triangles in general, about specific kind of triangles, and series triangle in general. Now we say, look, take this triangle, and then we kind of repeat the claim with respect to this particular triangle, and that's called specification. Diarismos, that's in Greek, I don't know if it's really best translation, specification. Then, of course, logically and mathematically speaking, the most interesting part and less trivial, we need so-called auxiliary construction or additional construction, right? As Kant stressed, we cannot just derive this theorem from definitions. We need something more. But that's not enough. When we did that, we carry out our proof, which is, you see, rather long. In that case, it refers to the previous actually theorem. It's all about equal angles of isosceles triangle. Okay, and we do conclusion, which basically repeats, but now we have the same claim, but already proved, as we say, right? And this is quadrat demonstrandum. Actually, Thomas Heath was right, translating here not what was required to prove, but to show, because there is these two words, deiknomy, apodeiknomy, and deixis, apodeixis, right? And when proof in this more narrow sense here, it's apodeixis. Right? And in Aristotle, all this thing about syllogistic, it's all about apodeixis. And Aristotle discusses this in Second Analytic, this difference between deixis and apodeixis. I will not go into that, but in Euclid, we have this verb deiknomy in the end. What was required to show, but not to prove, because proof is just more specific, is that part. And what the whole thing does, it shows something. I think in English would be something like monstration, demonstration and monstration. So this quadrat demonstrandum was just, I don't know who is responsible for that, but that was mistaken Latin translation. It should be quadrat monstrandum, not demonstrandum. Okay. Yeah, and but interestingly, here things look familiar, right? We have claim, we do something special, which is called construction, and a logician like Hinticke and many other may wonder what is this construction in logical terms. But anyway, the picture is clear. But here we have a problem. Everybody knows first problem in Euclid, to construct a regular triangle, right? And here we have the same structure. Even we look, it's not a theory, right? It's something specific. By the way, usual way to conceive of it, it's only in some as a as an order or perhaps question, as some people argue. I think that was Hintiker's view. It's kind of questioning. But I think again we may just drop these modalities. It's in my view it's better to look this again as kind of abstract operation, just without any modality, whether deontic or any other. But that time it's not primitive. It's operation which is not primitive, which is constructed on the basis of primitive ones, right? And so again we have this specification which works similar in that case. We carry out construction on the basis of this primitive operation that is postulates. But then interestingly, that's not the end, because you may say, okay, the whole thing you split, there are theorems which derive some further propositions from primitive ones, and there are kind of problems which builds more complicated objects from primitive one. But it's not like this in Euclid. The two things really interact, because when you did this, you accomplished that. You say, okay, this is primitive object. We build on the basis of this primitive operations something. No, there is no explicit rule of combining operation that we would need to introduce explicitly. But you may say, okay, it works somehow, but that's not the end of the story, because we need a proof. And proof that probably also answers to this marker question, right? That problem is not just about to bringing thing into existence. You see, there is this, if you like, propositional aspect of problem. So we need to prove that what we obtain that way is really what we say we obtain, right? And just referring to this procedure is not enough. Something else, and here we use this first axioms. So we have this parallel movement. First we work with just objects, and second we work with propositions, even if they very close. Just precipitating what follows, think about Curry-Horvath correspondence, right? That's kind of Curry-Horvath. We produce our triangle, and now we proceed related propositions, and that just works the same structure. Okay. Right, and again, right, we have conclusion, and it was requires to do, not to show something, but to do something. So I think I finished with Euclid at that point. No, I just say that usually this logical analysis is, our colleague John Muma, for example, right? When people talk about logical analysis, say, of Euclid, usual way, they say there is kind of logic behind it, right? It's not explicit in Euclid, but it's behind it. So we should reconstruct, find it. And by logic, in that concept, people usually mean something that manages propositions in one way or another, right? And I believe that it just not, it can be done as a kind of game, but if you look seriously on Euclid, there are both historical argument and theoretical argument, which are developed later, saying that it's just not good approach, it's just simply not relevant. We do have something like proposition, but in this interesting, this kind of regional logic using Husserl's term, right, which applies just for mathematics in form of axioms, and we have this constructive or objectual, if you like, part with postulates, and they work together. And actually, question I did not, and I don't have still good answer, how really these things relate to each other. Well, I have answer from Kari Howard from homotopy type theory. That's I'll try to develop. But how it really works in that case, perhaps it's just should be further studied. Perhaps there are some interesting evidence for giving some non-trivial answers about Euclid in that respect. Right, that I already mentioned. Right, and the last thing related to Euclid I would like to mention is that this scheme, which I just presented, which works both for problem and theorem, is not something archaic and dead. If we take here I took theorem from textbook by Kolmogorov and Fomin on functional analysis. So theorem here, and try to fit it into this form, and it really fits very, very smoothly. And I think it's more or less typical. I did not, of course, make any statistical efforts. Any closed subset compact space is compact. That theorem, right? That enunciation. Exposition here in this square bracket, everything I added, and everything else is in Kolmogorov's text. The exposition, let F be a closed subset, blah blah, and specification. No, there is no this formula. I say that. By the way, that's very interesting point. I think that Euclid always used this first person in specification. So if you like, that gives some idea that exposition amounts to specification of your object, right? And specification specifies so-called your subject, because here you just speak as common knowledge, as kind of universal spirit, Hegelian, and here only I say, I Euclid say, and I point here. So this specification on object and subject just work. Okay. But of course we don't find that in Kolmogorov, but then follows construction, which there is nothing like postulate. So we add something. Okay, I will not go. It's very simple, but I have no time to explain. And then we have proof. So it's just one line, very simple in that case. No, and of course conclusion they don't repeat because it's very simple theorem. But if one is required, I may easily repeat it. So it looks like this form is really pretty much alive in today's mathematics. It's not something we really should forget about. Okay? No, so I think I finished this part, and I go to Hilbert. Of course, there are many things interesting historically in between, so to speak, and Hilbert also is not alone in end of 19th century. As I mentioned, there are interesting other trends, but I just perhaps try to make this contrast, not discuss other things, because otherwise I'm lost. Okay, that's from his lectures when he basically prepared what became Grundlagen. So he says, okay, he talks about geometrical facts as kind of real facts, but what I want to stress here, it's only here. Right? I say geometry is science whose essentials are developed to such a degree that we may organize them logically. It sounds like he believes that there is kind of logical order of nature, of wherever this geometrical stuff belongs. That if we, make facts clear, they kind of naturally would organize themselves into logical system. It sounds like, of course, it's not very, critical approach, but looks like you believe something there. Look, principal thing is here for me, and of course Hilbert is not alone. It's not at all specific for Hilbert. This idea, what I mentioned in the beginning of my talk, as this assumption of what theory is. Of course, it's not specific for Hilbert. I think everybody would mostly say something similar in 19th century, right? But I think it's of our special interest how this idea develops in Hilbert. No, at least because Hilbert became so important and his approach became, kind of standard. That's why we pick up Hilbert, even if this is not his invention, of course. It's not his original thought. But we'll see later. Yeah. And here, no, I will not explain, of course, how his idea of formal axiomatics, I think everybody knows here. But I just would like to stress something which I think it's not always stressed and important for my story. And this is distinction, I would say, between logical and non-logical terms. He would not use that language, but in correspondence with Frege actually gave him this objection. If you don't have, how to say, if your words don't have meaning at all, then you're absolutely free, that is just hubris, how you call that axiom. And the whole point why it's not complete hubris is that there are certain points, certain words or expressions with fixed meaning. That's the whole thing for him. This idea of being schematic, schemer, and all these quotes, and his approach of being formal just rests on the thing that that the form expression is logical form. It's not any other form. It's logical form, and what provides this logical form is logical terms with fixed logical semantic. And that's how it stands in Hilbert's text. And here it's how we may, paraphrase it, say, for making even again closer to, for using some apparatus of logic. Case of variables is very interesting, and it's discussed by Tarski, that actually when we try to distinguish what is logical, what is non-logical, we have some kind of intermediate case, and Tarski somehow improved this idea. And this is variable. You see, in a sense, they just belong to logic, but in a different sense, they receive these semantic non-logical values, and in that sense, they are kind of joins between logical part and the non-logical part. So that's fundamental to that approach. And that is going to be changed, say, in homotopy type theory, exactly, where, and in topos theory, where we have non-logical semantic for logical terms. That's something which is really, if you just do it formally, you may ignore that, or you say, okay, I'm just doing models, semantics, that I don't care. It's logical, I leave philosophers to think about it, all right? But of course, it just changes absolutely the whole sense of, say, formalization, of being logical. Right, I just said more or less this. And that just Jakob Hindeke's comment, that he says, the basic clarified form of mathematical theorizing is logical axioms system. So there is this strong epistemic idea, of course, that logic somehow is a base for mathematics. Of course, it's not logicism, say, in Russell's sense. It's not an attempt to reduce mathematics to logic, say, right? But no, say yes and no. In a sense, even if you write these formal axioms and they completely open to interpretations, what you remain with is more or less that picture, you see? And what it does mean being purely logical? It allows for non-logical action. It does not mean that your every axiom is tautology, logical tautology, not of course. Yeah. But still your only say rule is logical rule of inference. You are not allowed to do anything else but infer certain proposition from other proposition. And of course there is the whole issue of, say, modeling, which I probably skip, and I think that's very interesting, and that's again in homotopy type theory. I think it's big open question, which is both mathematical and philosophical. What is exactly modeled? I think, by the way, in this kind of controversy between Vladimir Voevodsky and Steve Aoudi is exactly that question, what you should call a model. You see, because it's really, you cannot just use this Tarskian notion. It just doesn't go through easily. And people do use, as a matter of fact, word model in logic in different senses. in categorical logic in particular. So if we come back to Hilbert, actually it's a very strange mixture. For me it sounds really strange. Because one idea that you may have usual intuition, the usual semantic for things like point and line, we would count not a mathematical model, but somehow interpretation at least, right? Then, of course, there is these things when we interpret one theory in a different theory. For example, we make arithmetical models for geometrical theories, Euclidean, non-Euclidean. That's second thing. And this is also, it's very interesting in Hilbert. He has this notion of Gedankendinge. So he says, okay, after all, we just may not need neither intuition nor interpretation in different theory. We just assume kind of individuals and we posit them to existence somehow through our axioms. He doesn't say it's really ontological commitment, rather not. Rather, it's kind of just mathematical game. So we may also make this. And then you compare these three, at least for me, it looks like really mixture of rather different things. But historically, somehow they all contribute to what Tarski calls model. And the important thing for Tarski, of course, that Tarski's notion of model and this idea of satisfaction, it only works with this standard notion of theory, right? Because satisfies the formula means making it true. And then you need such a semantic that allows formula being true, right? So you should interpret your formula as a proposition first, something that admits for truth values. All right. Now I very briefly I make kind of development because Hilbert's view was developing. He worked all his career on that stuff, and that's there were several crucial points in development of his project, and I think that very important crucial point when he decided to axiomatize logic, and that's by the way what Hintikov was deadly against it. So he says something like, okay, we axiomatize the theories, and now it's like next step, axiomatize logic. Jakob Hintikov says, look, if this idea of axiomatization I just described, right, it just assumes that logic is kind of last resort, it's kind of fixed. So, and then we fix logic in order to axiomatize something else, right? And what would it mean axiomatize logic itself? What would it mean we have some stronger logic behind or what? So Hintikov just believed the idea was not coherent. It's interestingly that Hilbert mentions Russell here. And of course, no, okay, I will not go to this discussion whether its idea coherent, but what was outcome of that, right? That of course was using kind of symbolic logic. Right. So I don't think that Hilbert really gave up his early approach. He rather developed symbolic logic and called that axiomatization. And axioms for symbolic logic, in his understanding, are tautologies which generate all other tautologies. It's a set of tautologies, and as we know through Gensen's work, of course, it's not necessary at all. You may just describe your whole logic with zero axioms. But interestingly, you cannot describe it with zero rules. All right? Here, Hilbert uses his Hilbert-Ackermann book of 1928, and there they use one rule, modus ponens, and a list of axioms. So axioms are dispensable, but rules are not. That's, I think, very important lesson. But next interesting reasoning, which important for our story, comes when he attempted now to use a symbolic logic for the same project, right? The whole thing of Grundlagen of 1899 does not use any symbolic logic. And now what happens when we do use symbolic logic, as people do today for axiomatic set theory or everything. And here he makes, because here we have this new game, right? We have this symbolic aspect which did not make part of this earlier project. And here is, I think you may know this quote, right? No? He says, mathematics cannot be founded on logic alone. Is a condition for using logical inferences, for performance logical operations. Something must be already given in our faculty of representation, certain extra logical concrete object. So what he means here, it's not that for mathematics we need more axioms, like for doing set theory, just logic is not enough, so we add certain axioms like axioms of set theory. No. What he says, this symbolic setting itself is a condition, you see? So it's not just, you know, some means of representation which we may drop somehow and forget about that. No, it's really foundation. That's his view at the moment. Right, and right, that's what for all science, he says. In mathematics, specifically in mathematics, he says, what considers this concrete science, this is our syntax, our symbols, right? Right, and that's, maybe I draw too much on that, but I read this passage as an expression of view that axiomatic method he's developing really should become instrumental. It's not just for foundations. It's something that, according to Hilbert, should be used, say, for publishing papers. No, he didn't say that, but maybe some of you object, but I take it become basic instrument of all research. So I think his vision, of course, you do need intuition. It does not mean that you are sitting and deriving formula theorem. It rather means that when you have good ideas, you should present them in this axiomatic form. And you should present your proofs, for example, as formal inferences. And we know that never happened. Anyway. So what is, if we now come back to Euclid, to this story, what is interesting here? That you see this logical proof through this turn through symbolism, it comes back to kind of construction, not geometrical, not diagrammatic in, say, Euclid sense, but symbolic, so kind of combinatorial, right? So this showing, proving things comes back to construction for doing something. No? Again, I have carried over it in mind. But I think that that's important, that you cannot drop this logical semantics. You cannot just say, okay, this is my syntax, which carries some important mathematical ideas somehow. But for that setting, it's important that it carries through prepositional form. From this notion of well-formed formula carrying preposition, being, I would say, admitting models through satisfaction, through truth evaluation, these things. Yeah, and of course, otherwise you cannot understand this big Hilbert program, right? To prove consistency, say, of set theory or some theory. So what you should do, you should show somehow that this combination of symbol is not obtainable through your combinatorial rules. But why it's important question? It's only important question if you say this is contradiction. If you just really look as a game of symbols something, you cannot give any significance to this kind of problem. You see, so that it's just for saying, and that's what really changes in topos and homotopy type theory. Really, this stickness to this propositional form is very essential. You really cannot take it out
from a proof theoretic point of view. You can derive everything from some statement like P and P. So it has nothing to do with semantics, but the rules of inference allows you to derive everything. So it trivializes the conclusions of your theory.
But it only because it's constructed in such a way that is contradiction. You can forget its contradiction. And when you say derive everything,
from a formal point of view, every proposition or every...
Now, it's not purely syntactic property. What you say now, it's not purely syntactic.
It's syntactic in the sense of proof theory. It's not syntactic in the sense of syntax.
It's rule-wise.
Not
Rule-wise, I mean, the rules might not be syntactic.
But it does not involve semantics per se.
Exactly.
That's just what I'm saying.
It's not because it's
No,
contradictory.
But at least for my reading, when you talk about semantics, right, it's very important to include logical semantics. Semantic for quantifiers, semantic for, and also semantic for being a proposition. It's also part, I think what I mentioned in the beginning of my talk, right, it's kind of hidden thing. If we say, okay, here are logical terms, here are non-logical, right, logical, as usual in books. And people would talk as if it would be pure syntax, but it's not pure syntax. Because you say, that logical, that is not logical, that's semantics. You see? Logical semantics. Oh, okay, well, it's very interesting point. We may come later, okay? Yeah. No, I briefly mentioned that, of course, we know that at least that part of Hilbert project really didn't work. That it did not become instrument of all research, and I think not because of big issues like Gödel's incompleteness and so on, but just because it's presenting anything like interesting theorem of kind I just mentioned, subset of compact spaces, closed subset of compact spaces compact, to present it in such a form, it's kind of theoretically possible. You may argue it's theoretically possible, and you may derive certain claims from this hypothesis or from that proposition that it is theoretical possible. But it's not something you may really work that. And I would just very, very roughly, because I think it's of course recognized, and people will say, but that's practical question, right? That's not really theoretical, philosophical question. And the practical questions are also important. That's why we would have philosophy of mathematical practices. But I believe that it's kind of intellectual compromise, because mathematics, it's a bit strange even to talk about mathematical practice, right? Mathematics is a theory. So everything that works in mathematics is, okay, it's further discussion, but I think that this distinction between theory and practice is really not very clearly construed in that case. And the real purpose, I think, for doing philosophy of mathematical practice is just, of course, I'm for studying it, of course, but I think describing it as a practice is kind of downplaying it. It's just for avoiding really serious talk with those people who have this, in my view, outdated view and incoherent view about foundations. When you say, I'm not talking about foundation, I'm talking about practice. So you go around. In that sense, I think that the issue is more serious than, and when you call it just practical, you kind of downplay it. Okay. And the only thing for which this method really proved to be very effective is, of course, all meta theorems, all meta mathematics, like independent of continuum hypothesis. But I would also to point to the fact that why we believe that continuum hypothesis is independent, right? It's proved, but it's proved not by formal mathematics. It's proved by so-called usual mathematics, right? That's very important. So it cannot be kind of foundational fact, right? It's our belief that that's continuum hypothesis is independent rests on informal mathematics. And you cannot just formalize it and formalize further. It just, no, we may discuss, but I think it leads nowhere. And Hilbert's view, of course, that it should not be formal, right? He just wrongly, erroneously believed that this informal mathematics, what he called, could be very small and kind of rather simple and easy. And that didn't happen. Here he was really wrong. Okay. So I conclude on Hilbert, and then I take another maybe 5 minutes for concluding about this constructive axiomatic method. So Hilbert architecture of axiomatic mathematics does involve what I was doing and show showing as well as Euclid's architecture. But unlike Euclid, Hilbert places these two layers into different theories. A formal theory is supposed to be purely propositional, right? And it carries its models. There is all problematics, well known. But this so-called constructive part, it goes to meta theory. And meta theory, he is not very clear on that, but I think it's supposed something like Euclidean style. So it's, it may also provide theorems, so we may have meta theorems, but it also have some like problems, right? To make or not to make certain symbolic construction, right? And of course, Hilbert, why he thought that project was important? Because he thought that that mathematics is kind of simple, as I just mentioned, right? So it may not involve any high infinities, or perhaps no infinities at all. This is his finitism. And we know that, of course, this part of project that didn't go through, and in continuum hypothesis, this forcing technique is not trivial, right? It's not elementary. So, but anyway, we use it. So this is really method works good for meta-mathematics, but bad for mathematics. So it's not, it's a good instrument for very specific research, which is called logical analysis or mathematics or mathematics, but not for doing mathematics. Yeah. Right, and the question which I would like to leave open after all this story is this. Here again, the basic notion of a theory is reserved for T, not for its meta theory. You say, okay, in meta theory we can make kind of something informal, something not very... But in theory, we are good in theory, right? And theory is this system of proposition, etc. But I think this whole picture and this view, retrospective view, it's already more than a century past, I think just does not give justification that this is a good notion of theory. That how is this formal theory is constructed that really fits, say, practice, or so there is no reason to believe it's a good one. So I rather think it's a bad notion of theory, and very, very generic. Theory is a system of proposition. Just if we go to Euclid, and then I'll show to recent stuff, it's clearly that it's not. And by the way, it also comes together with what's going on in philosophy of science, the so-called non-statement view on theories. Because all attempts to use axiomatic method in this form in science actually basically failed. And some people, like Patrick Supis, for example, he, in my view, correctly saw the reason for this failure exactly in this assumption, that theory is a set of proposition. It's a different way, that his way to treat this problem, right, was also just providing set theoretic models. I think it didn't work either, but that's a different story. Maybe in the end of the second talk I'll come to that. Okay, and so now what I think may be remedied is the so-called constructive axiomatic method, and I find that is partly gained by Hilbert. So I began to work on that. I kind of was fighting Hilbert, but as usual, after all, I found that Hilbert was very well aware about this problem, and I think had very good ideas how to treat it. All right. Here there is rather big literature, it's so-called genetic method, and that name comes to Hilbert's early paper of 1900, where he provided a formal theory of arithmetic, his version. Right? And so then he discusses his approach to axiomatic method is still very new, is nothing like common at that time. So he wants to defend it and to explain it. And he uses this, what he calls genetic method, as a kind of opposite, to make a contrast. And genetic is basically that certain mathematical objects are built from other objects. And very interestingly, that he apply it for real numbers, for Dedekind cuts, and for Cauchy sequences, which are not constructive in anything like usual sense, right? So constructive here does not mean anything like recursive, algorithmic, you see, Leningrad principle by Markov. But here constructive just means making objects from other non-propositional objects, right? So we begin with like Dedekind cuts. We begin, we say, with natural numbers, we build rational numbers, and then we're making these classes of rational numbers, no matter that these classes, that is not something you can really, how to say, do syntactic, algorithmically. Of course you can, but it's still this idea, right? So Hilbert described it as genetic in that case. And I think that's very interesting. That's, by the way, why I find it interesting that just like in axiomatic method, you should not fix axioms, right? Axiomatic method just gives you freedom to apply any axioms and any system of logic, and I think it should be the same with constructive. So these notions like Bishop or Markov, they just fix certain rules. They say this rule means following these rules means being constructive. If you violate them, you are not constructive. But I think you should really have this framework of being constructive, which allows for changing rules, just like axiomatic method. And I think that can provide this. You see? So he says, he does not explain. He just says, despite high pedagogical value, this axiomatic method is better. And here already I think it's very interesting quote which inspired me for this whole thing. It's already from 1934. So his mature vision of the problem. It's rather different from 1900. You'll see. So he says, the term axiomatic will be used partly in a broad and partly in a narrow sense. We will call the development of theory axiomatic in the broader sense if the basic notions and presuppositions are stated first, so it's very general, and then further content is logically, he says, logically derived, right? In this sense, Euclid, Newton, and Clausius, they're all axiomatic. And then he says, axiomatic in a narrow sense, existential form. It's like existential propositional form, right? It's, as you say, with possibly free variables. Comes as an additional factor. This marks the difference between the axiomatic method and the constructive or genetic method. Here it's not very clear, of course, because if we say constructive and genetic are mutually exclusive, then it's not very clear how he would call, say, Euclid axiomatic, right? So there is, but as explained, while the constructive method introduces the object over theory only as a genus of things, an axiomatic theory refers to a fixed system of things. You see, given as a whole, except for the trivial cases where the theory deals only with finite and fixed set of things. This is an idealizing assumption that properly augments the assumption formulated in the axioms. So I read it, for example, in postulate. When you read postulate constructively, right? For given 2 points, there exists a line. This would be existential form, and then you need some semantics. You need somehow these points on lines somehow exist somewhere. That's what he calls this idealizing assumption. And if you do genetically, you do differently, right? You don't have any existential proposition. You just produce a line, something like that. And it's interesting because here is a comment. I don't know if this English translation really appeared because of Grundlagen of mathematics. It was edited, just translated by some German people, then edited by Gabay and some other people. And they here they have interesting footnote. They say, no, it's still Hilbert, sorry. Euclid, so Hilbert says, Euclid does not presuppose that points or lines constitute any fixed domain of individuals. Therefore, he does not state any existing axiom either, only a construction postulate. Right? And here is this footnote. They say, unless we see construction as a state-changing process, this remark is not justified. From a static logical point of view, existence sentences are always implied by construction postulates. It's what Gabay says. And I think he is right. And if I want to read Hilbert and Bernays charitably, so not assuming they are idiots, I think they do think about this Euclid construction as a what Gabay calls state-changing process, as a genetic procedure in that sense. Because the standard reading of this passage, I think we have some talk with Dirk Schlim on that, is that from 1900 to 1934, Hilbert changed his view in the sense that in this later period he called constructive or genetic method just a contentful version of his method, right? So it's still axiomatic, it's still proposition based, but it's not formal, right? It's fixed geometrical semantic. But I think that is really direct evidence against that. That if you take that view, right, you should really say they say something incoherent. So I rather believe that they really take this difference quite seriously, and they don't think about these constructions as some inference, propositional inferences. Right. No, and so it's given that Hilbert qualifies theory as axiomatic in this broader sense, given that identification of broadest axiomatic with the received notion of axiomatic is erroneous, we may conclude that the broadest axiomatic, this constructive, is broader than the received axiomatic and includes the genetic. Right. And actually, what is kind of common ground? So project here, as I understand it, is synthesize, is combine genetic and axiomatic, if you like, right? And what could be common ground? And I think it's clear what can be common ground is this notion of a rule. So you have logical rule, but you also have non-logical. No, it depends what you call logic. Say, you have propositional rules about proposition, how to handle propositions, and you also have rule how to have objects of different types. That's the idea, and we'll see in homotopy types, you at least realize precisely. So constructive, I repeat, maybe axiomatic theory in that sense comprises non-propositional principles similar to Euclid's postulates, which allow for building and operating with non-propositional objects, and not only with formal expression telling us something about these objects. While usual, that's what very important is the following. While usual notion of constructivity in logic and mathematics specifies such rule, I leave it open, my point is the next. In constructive theory, propositions are object of special time on equal footing with non-propositional objects. That really makes difference. That was, of course, long before homotopy type theory. Martin Löw had this view already just for his type system. Objects of this type belong propositions and objects, non-propositional like triangles, they just make part of the same theory. And that's what we see somehow in Euclid, even I say, for me at least it's not completely clear how they combine, but it's of course, they just make part of the same theory. And in Hilbert's case, they are put one into theory, object theory, and another to its meta theory. So I'll show that this broader notion of theory, which allows for proposition and non-propositional objects, and rules which are valid for both these different types of objects, that is something that in common between Euclid and homotopy type theory. Yes, That's what I'll try to show next time.
Merci. On a plein de temps pour la discussion. Est-ce qu'on fait une pause pour un café? Hein? Ouais, une petite pause puis on fait la discussion après. Bon, super. Café.